Assalamu alaikum. My name is Hussein Abdul Karim, and today I'm going to present my part in Bernoulli's experiment. So let's start with introduction. Introduction. Bernoulli's theory states that an increase in a fluid speed occurs at the same time as a decrease in static pressure or a decrease in the fluid's potential energy in fluid dynamics. The theory was first published in 1738 by Daniel Bernoulli in his book Hydrodynamic. While Bernoulli deduced that pressure decreased as flow speed increased, Leonard Euler was the first to prove it. While Bernoulli deduced that pressure decreased as flow speed increased, Leonard Euler was the first to derive Bernoulli's equation in its current from in 1758. The theory only applies to isentropic currents in which the consequences of irreversible such as turbulence and non-adiabatic such as heat radiation processes are uh, minor and can be ignored. Problem statement. The problem statement of this experiment is the aim of this experiment is to see if it can prove Bernoulli's theorem. Next, there is no instruction about how to conduct the experiment. The data can be affected if experiment contains errors. The objective of this experiment is to develop techniques for analyze fluid flow in its nature, and also to test Bernoulli's theorem in experimental settings for physicus and embodied fluids. Analyze theoretical and experimental research results related to Bernoulli's theorem. So, the scope of this experiment is that only incompressible fluids were used in this experiment. This experiment's equation must account for the fluid pressure losses. That's all from me, and thank you.
Hello, my name is Basilin. I'm going to present chapter 2 of this experiment, which is the theory. Firstly is the introduction to Bernoulli's theorems. Bernoulli's theorem is the relationship between the pressure, velocity, and elevation in a fluid, which is include gas or liquid, and with no energy exchange due to like dissipation, heat transfer, or any sharp work. This Bernoulli theorem is tested based on the conservation of energy principles. In this Bernoulli theorem is assumes that frictionless, steady, and incompressible, which the fluid from the narrow channel. As a result, the kinetic energy rises as well. So the increase in kinetic energy is due to the net work done on the fluid to drive into the channel, as well as the work done on the fluid by the gravity if the fluid change in a vertical position. Bernoulli equation states that for incompressible or frictionless fluid, the following sum is constant, where P is absolute pressure, and the rho is the fluid density, V is the velocity of the fluid, H is the height above some reference points, and G is the acceleration of gravity. So if the subscript 1 and 2 refer to any point along the face of the which is where the fluid travel actually, and the Bernoulli's equation become this equation below. The last part is the application for Bernoulli theorems, which is first is the attraction between two closely parallel moving boats or bus. When two boats or buses travel in the same direction in the water, or A between them travel faster than the water on the opposite side. So as the result of Bernoulli's theories, the pressure between them is decreased, and they are drawn towards each other due to the pressure difference or resulting in attraction. The second application of Bernoulli principle is working of an aeroplane. The shape of the wings of the aeroplane as shown in the figure. Due to the specific shape of the wings, when the aeroplane runs, air passes at higher speed over it as compared to the lower surface. This difference, A, speed above and below the wings in accordance with Bernoulli principle, will create a pressure difference. So when the force become greater than the weight of the plane will rise up. This is how the application of the Bernoulli principle in an aeroplane. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syarudin bin Sharifuddin, MA 17103. I'm going to brief you about the method and the procedure for the experiment 1. This the procedure. First, the vent is open. Second is the motor pump turn on to let water flow in the manometer tube, then air bubble will be released. Third, the manometer tube check for any leftover air bubble. Fourth, the volume was adjusted by the control valve. Next, the reading taken as a baseline. Next, the time taken of the water flow rate for the tank to be filled up to the 5 liter, until the 5 liter. Next, the hydromic tube move until the cross section one of the venti tube reach at the end. Next, the flow rate and the time taken measured and recorded and tabulate. Next, the step which is 3 and 8 repeated for the cross section 2 until 6. That's all. Thank you.
Ya, Assalamualaikum warahmatullahi wabarakatuh. My name is Farhana binti Muhammadi. My ID is MA 709. So I will present chapter 4, which is results and discussion. So next is figure 1, shows the experimental apparatus. So we have a Venturi multi-tube manometer and pipette. So next, step 1 shows the internal diameter of multi-tube manometer that has been recorded during the experiment. However, the area of each multi-tube manometer needs to be calculated. Formula to calculate the area equal to pi multiplied with r squared. So we got this area by calculating the radius, and we got radius 14.2 mm. Finally, we get the area 6.33 for the point 1. So next is static head calculation that we calculate, and step B is total head. So we got this. The next is the formula that we use to calculate the measured data. So finally, this is a calculated data, and we got the value. This is a graph. So this is a result for this experiment. Firstly, we got the graph one is represent the static head versus Venturi meter point. So based on the graph 1, static head value is maximum at point C, and the value is 210 mm. So the value starts decreasing from point 1 at 180 to 30 mm at point 3. As you can see, this drop. And then it begins to increase again until it reaches the maximum value at point C. So next this is graph 2, which is titled head versus ventrimeter point. So this graph shows the value of titled head against ventrimeter point, where the value is firstly decreasing from 0.1 to 0.2 with 185 mm to 100 mm respectively. So the value continue to rise again until 0.6, where it contributes the highest value, which is 215 mm. As you can see, this is a 0.6 and this is the value for the 215. So next, for the graph, from the graph 3, which is dynamic head versus ventrimeter point. So we can see that the graph has a maximum value at 0.3. This is a maximum value, and which is the value for this point is 95 mm, and the graph start at which the value of the limit is equal to 5 mm and also with a value of 5 mm at 0.6. So we can see the graph is said to be normal distribution as it in positively skewed condition. This is graph 4, which is represent the pre-measured and ventrimeter point. So this graph 4 shows the measure P and ventrimeter point. As you can see, from a simple survey, the graph shows an increase from 0.1 to 0.3 and start to decrease with a linear inclination until the last point, which is 0.6. So the maximum value of P measured lies at 0.3. As you can see, this equal to 1.652 meter per second. Next, this is graph 5. Based on graph 5, these two critical points for calculated P values we lies at 0.2 and 0.4, as you can see, and the maximum value of calculated P is at 0.4, which is 0.8621, and the minimum point is at 0.3 with a value that is equal to 0.1298. Next, this is a last graph. This result shows the dynamic pressure versus ventrimeter point. So for this graph, we can see that the highest data lies at a 0.3, and the value for 0.3, which is 932.0 Pascal, and the lowest value of dynamic pressure lies at 2.6, 0.1 and 0.2 at a value equal to 49.1 Pascal. So that's all from me. Thank you.
Assalamualaikum. My name is Haikal bin Alia, and I will be presenting the chapter 5 of Bernoulli's theory. Conclusion. For the conclusion, the aim of the experiment is to investigate the relationship between the velocity, area, and pressure as described in Bernoulli's equation. The density of the fluid is stable in the experiment, and the net friction force should be zero. We should deduce the result for the flow obeys the Bernoulli's theory. The findings in our experiment indicates that the velocity increases as the strain decreases. Nevertheless, the graph of total head versus flow rate indicates that the flow rates increase and the head does not follow the Bernoulli's law, which may not be influenced by certain error such as equipment failure, human error, and external variable. Lastly, we should assume that the goal in this experiment has been met as the data follows the Bernoulli's equation theory. Thank you.